Okay, let me begin not by thanking the organizers for scheduling me after the wonderful experience last night, but thank them for everything else. I also want to thank the participants. I think one of the best things about these meetings is the interaction with other people where you talk about mathematics and you say vague things that are actually inspirational, okay? So there's several people in the room here who have done that for me, Franz Forstneritz and Ming Xiao, and someone who over the years, and Howard Jacobowitz, who have said something that's motivated me to even talk about this kind of thing. So let me say, about 6 months ago, I gave a talk called Rational Sphere Maps for the n+1st time. As many of you have realized, a lot of my work years ago was on stuff that you care about. Now my work's on stuff that only a handful of you care about. So I felt I'd spoken about it too much. And so I was going to give a completely different talk. But then I made some progress, which I want to talk about. So by induction, I have to correct my title to make it Rational Sphere Maps for the n+2nd time. Okay, so let me remind you, basic question in CR geometry. I have CR manifolds M and M prime. And I want to determine all the CR maps between M and M prime. Now, most of the time, the only maps are constant. Yeah? So in cases when there are many maps, it becomes more interesting. So there are lots of circumstances in which there are many maps, but the ones of interesting to me is a special case of the unit sphere. After knocking myself out on weakly pseudo-convex domains for years, it's really great to have the unit sphere, right? Okay, so let me remind you of the definition. A rational sphere map is simply a function from complex n space to capital N space, away from the singular locus of the denominator. So P is a polynomial, Q is scalar valued. It's always assumed reduced to lowest terms. Q of 0 equals 1, doesn't matter in this talk. But I'm always assuming F is holomorphic on the closed unit ball. And thus the denominator is not 0 there. And the crucial point is that F maps the unit sphere in the source to the unit sphere in the target. So you might say, big deal, who cares? But many years ago, I proved the following theorem, which used operator theory actually in the proof. Suppose I have an arbitrary rational mapping that maps the closed ball. So here's the closed unit ball in the source. Here's the unit ball in the target. Suppose I have an arbitrary rational map that sends this to this, strictly inside. Then no matter what it is, I can find an additional collection of polynomials that I call G, so that the original P over Q, P plus G over Q, is a rational sphere map. So this means that if I allow the target dimension to be sufficiently large, I can do anything I want. So the way to say this is there are lots of rational sphere maps. Okay? On the other hand, as we'll see in the next slide, so two examples illustrating this theorem are sort of trivial, but make the point. Consider the function lambda z1, z2 in the closed unit disk, closed unit ball rather. It maps to the strictly inside the unit disk if lambda's absolute value is less than 2. So I can find polynomials to make that the first component of a rational sphere map. There is no formula that's independent of lambda. In order to get the minimum degree of the example and the minimum target dimension of the example, those numbers both go to infinity as the absolute value of lambda goes to 2. And let's look at the other one, similar, for same lambda and appropriate C1, that function maps the closed unit ball to the unit inside the unit disk. So I can find that's the first component of a rational sphere map. But both the degree and the number of terms go to infinity the closer this variety of 1 minus lambda z1, z2 equals 0, the closer this variety gets to the sphere. So this is a serious analysis situation. Okay, now, a rational sphere map is called minimal if its image lies in no affine subspace of lower dimension. And the idea of this talk is I'm going to consider various results like this. I take some collection of rational sphere maps with some property, typically group invariants or group equivariants or something else, and then I ask, What are the possible target dimensions for maps in that group? Of course, once it's anything, it can be anything bigger, so I call it minimal if we're only considering minimal maps, the minimum target dimension, okay? So the starting point for discussion is that everybody knows these things in this room, I'm sure, but let me say them anyway. When capital N equals little n is greater than or equal to 2, the only rational sphere maps are linear fractional transformations. So they're minimal if the target dimension has to be the same as the source dimension. Okay? Another result is if you have a non-constant rational sphere map, it extends to be a proper holomorphic mapping between balls. Okay? And hence, the inverse image of a point is both compact and a complex variety. So there aren't any positive dimensional subvarieties of the ball. So therefore, the only possible thing is that the target dimension is greater than or equal to the source dimension. Now, let's get to the next point. I don't know, it's almost 50 years ago when Sid Webster was studying Chern-Moser invariants, and he proved the following theorem. You have a sufficiently differentiable, I don't remember the differentiability requirement, but F maps the sphere S2n minus 1 to S2n plus 1. This is a sufficiently differentiable CR function mapping. Then after automorphisms, it's Z plus 0. So you're just mapping the sphere, or a ball if you want, into the sphere goes into the equator, the higher dimensional sphere. This was proved a long, long time ago. And then Farron is a great hero of mine. He did two things with this result. He showed that Webster's theorem required the source dimension to be 3 or more, and this theorem's false if the source dimension is 2, and Farron wrote down the 4 equivalence classes of examples when the source dimension is 2, and that was what motivated me to leave points of finite type to think about this problem. I was just delighted. I saw these 4 Farron examples, and I asked myself the question, what is it in all situations? What are all the polynomial sphere maps, and so on? And I thought it'll take me a couple years. You know, more than 35 years later, I'm still at it. Okay. But anyway, Farron also he extended Webster's theorem in a second way. If the target dimension is not too big, remember in Webster's, you've got the sphere and then a sphere in one larger dimension. You conclude the mapping is basically Z goes to Z with 0. Farron extended that result when the target dimension is strictly less than the number 2n minus 1. Okay? So there are gaps in the possible target dimensions for these maps, right? For rational sphere maps. Okay, so anyway, now I want to mention something that's important for the rest of the talk. This is some work I did with Ming Xiao. For this very general setup, I have some sets, M and M prime, and they have automorphism groups and so on. And I can associate it to so I just assume M and M prime are spheres, and I have a CR map between them. Then you can associate 5 groups, at least, but these 5 are what we did, to the map. So the first one is it's a subgroup of odd M cross odd M prime, consisting of those pairs alpha beta such that F circle alpha is beta circle F. Now, someone asked me if I were an algebraist or an analyst, and I said, well, I'm a mathematician, so I'm both, whichever is relevant. Ming and I didn't say this the second way. We just said gamma F, well, sorry, we said it the first way, that gamma F is the set of alpha such that there exists a beta. So an algebraist friend of mine pointed out to me, why don't you just say it's the projection of AF onto the first factor? Okay, so that's how algebraists think. You can also take a projection on the second factor, and then fifth, and then there's invariant groups. So the first work on invariant groups in this case goes back to Franz Forstnerich. I'll say a bit about that in a second. But the source invariant groups, the only one that arises in this talk, is a set of alpha such that F circle alpha is equal to F. So now the question comes to this. I have unit spheres, I have the rational sphere map. And now I make some assumption about these groups. Then I ask the same question about the gaps. How does the set of gaps depend on the group? That kind of question. Okay, so let me just answer this first thing about the invariant groups. So this is an old theorem now, a long time ago, based on work by Forstnerich and Lichtblau, my student. There are actually only three possibilities. So remember, F circle gamma equals F. Gamma is in some subgroup of the fixed points free subgroup of the unitary group. The mapping Z tensored with itself m times is invariant under replacing Z, which is a vector, by omega Z, where omega is a m through to unity. That one's a standard thing. Will come up a lot in this talk. The second one is really a fascinating thing. When you have an odd root of 1, you represent it by matrices like that. The quotient of the sphere is a certain kind of lens space. There is a non-trivial example in this case. There is only one other example that's possible, and it's rather stunning. There exists a proper map from the 3 ball to the 17 ball, where 17 is minimal, that's invariant under this group, where omega is a 7th root of unity. No other examples are possible. Okay, so anyway, we're going to answer the questions for these groups. Now here's the answer, sort of. Okay, go back, explain which notation? Oh, what is Z tensor M? Okay, as many famous mathematicians have asked me the same question. What do I mean by this? So it's a good question. So what I'm going to mean by this is just simply a list of all the homogeneous polynomials of degree m, never repeated. So this is alpha is equal to m, and the sum of C alpha squared, well, let me just write this. The norm, so if you're in a Hilbert space, the square norm of a tensor product, you have that identity, right? That's always true in Hilbert spaces, right? So you just simply list all the homogeneous monomials, and C alpha squared is the multinomial coefficient m choose alpha. That comes from expanding this guy. This is obviously true. You expand this guy, multiply it out by high school math. The coefficient of mod Z to the 2 alpha is m choose alpha. Okay, so it's, I don't want to use words like symmetric tensor product, but okay, that's what I mean. Okay, so now let's go to this thing. So for gamma m1, that means in this notation, I'm assuming the source dimension is 1. Now that's much easier than what was considered by Jennifer Brooks, Sean Curry, Dusty Grunmeyer, Purvi Gupta, and 3 of their students in some special program. They actually did this, and when it's combinatorially a lot harder when the source dimension is 2, but in some sense, the source dimension 1 fits with what I'm doing here. Now, they also conjectured the answer for that second group, and I wrote out proof, which I have in these slides, that the only possible target dimensions for a minimal map invariant under the second group, it's either r plus 2 or any number greater than or equal to 2r plus 3. So there's a gap, right? Anyway, that's the result. But now, for the group with from the 3 ball to the 17 ball, there's a new phenomenon, to quote Jeff McNeil, that's his favorite phrase in math. All numbers at least 37 arise as possible target dimensions. The numbers 0 to 16, 18 to 28, 31, and 35 to 36 are gaps. Now there's a slight gap in what I said. I wrote down explicit maps from every degree, in every degree except those numbers, from adding to infinity, but sufficiently many that proves that it's true for all numbers, except my proof for 35 and 36 non-existence is not complete. And Dusty Grunmeyer seems to be very close to filling it in. And I'll explain why. I want to say something about this before I get to the next point. Okay, so let me just repeat the first one. For that particular group, that's the answer. The only possible numbers are r plus 2 or any number at least 2r plus 3, and that's consistent with a conjecture that the 7 of them, is that how many people were in that group, is consistent. But for the other group, the one with this one, the new phenomenon arises. I want you to stare at this polynomial for a minute. If I look at this group and I write down a basis for the algebra of polynomials invariant under the group, I call the variables x, y, and u, much to the horror of my co-authors. I don't want to use z because z is a complex variable to me, so I use x, y, and u. But anyway, look at the first line and the second line. All the monomials that occur there, together with the constant function 1, generate the algebra. But in the third line, you get products of those terms. Okay? So you notice, for example, x4 yu squared is xyu times x cubed u. Or x squared, whatever. Yeah, x cubed u. So the last 4 monomials have to be there to have a monomial sphere map or rational sphere map. They have to be included. But they're annoying because they're products of previous ones. So when you do operations on this map, you might get terms that merge together. So it becomes extremely difficult to calculate how many terms there are. Now, I want to pause and say something that shocked me, and I don't know if anybody knows this fact, but I learned this in thinking about this kind of thing. So when you have positive coefficients and you multiply things together, it's pretty obvious what happens to the number of terms. But when you have negative coefficients, it's not so clear. There exists polynomials in one real variable. Okay, this is unbelievable. With a property that p squared has fewer terms than p. If you can write one down for me, I'll be really impressed. They exist. But think about that from high school math. Some polynomial, you know, summation a j x to the j. You multiply it together. Can you imagine trying to work it out so that, right? There's a whole, you know, some big variety, you know, but it's true. And people in number theory have actually just studied this problem. And so on. There's a lot to say about that. But the problem with this group is you could, in principle, introduce negative coefficients into the thing and do certain operations where the negative coefficients go away because of this possibility that there are these products. Okay, so I claim this thing deserves additional study. What I'd like to see is the San Diego crew take the 3-ball quotient by this group and prove all sorts of wonderful theorems about it, because it's something new. Really new. Okay, now I'm going to start finally getting to the talk after 20 minutes. Andy told me he's running a tight ship. Okay, so Ming Xiao and I proved several theorems about these groups. The first one, this equivariant source group is non-compact if and only if the map's a linear fractional transformation. So we've already seen, okay, let me say that these 4 theorems. The group is unitary, is the unitary group, natural group to study, if and only f is an orthogonal sum of tensor powers, where at least one factor has m at least 2. And the other one, which is the main theorem for this talk in a way, this group contains a torus, if and only if f is spherically equivalent to a monomial map. Now, Yuji Lebel and I spent a lot of time playing around with monomial maps. We're going to do a little more of it today. You know, and sometimes people say, oh, monomial maps is a special case. Actually, it's a decisive case because of this theorem, right? Now, there's another theorem we proved that has nothing to do with this talk, but I would suggest if anybody's looking for a problem in this area, if L2 estimates and finite type and things like that are driving them crazy and they want a problem on a completely different field, okay, play around with this. If G is a finite group, there always exists a polynomial sphere map whose group gamma f is G. and it's actually quite hard to prove this, even to find an example where the group is trivial group, you have to do a little bit, okay? But anyway, these have some consequences. So I want to consider the unitary group first and show you the gap situation there. So the maps are Z tensor to itself D times for D greater than or equal to 2, or orthogonal sums of such maps where at least one factor is 2. Now these maps are monomial maps, of course, because the unitary group contains the torus, right? But anyway, we're interested in their possible target dimensions. Okay, so here's what happens. Suppose the source dimension is 1. Then every target dimension is possible for a minimal map from the unit disk, right, or from the circle. No restrictions. If the target dimension is 2, the only restriction, the numbers that can occur are 1 and 2. Every number 3 or more occurs. And it's simple because the mapping, I should thank John for asking the question. I'm listing all these monomials. So when the source dimension is 2, the dimension of the space of homogeneous polynomials of degree m in 2 variables is this m plus 1. So I have to have a factor of at least tensor twice. So the answer here is possible target dimensions for minimal maps are every number at least 3. 2 doesn't arise because the equidimensional case has to be an automorphism or linear fractional transformation. The group is not the unitary group, right? Okay, so that's the result. Now I want to go to the next one. Okay, if n is 3, I have this ridiculous list down here, 1, 2, 3, 4, 5, 7, 8, 11, 12, up to 50. Every target dimension for a minimal map occurs except this exact list of numbers. Okay. Now, above it, you'll see a shorter list. Now, the shorter list is something that many of you might have heard of in recreational problems. You consider triangular numbers, k choose 2, like 1, 3, 6, 10, 15. And you ask, what numbers can be written as sums of distinct triangular numbers? I've seen this problem a couple times on prize exams, and not the Putnam exam, but things like that, one in Canada. Okay, well, the answer is everything except 1, 2, 3, 5, 8, 12, well, sorry, is everything except 2, 3, 5, 8, 12, 13, 23, and 33. And it's not a trivial thing to prove, but you can do it by elementary math. You have to do some inequalities and so on and so forth. Okay, now what happens here, though, is if you have a monomial sphere map that doesn't take 0 to 0, it's an elementary lemma that there exists an automorphism of the target ball such that the composition is still a monomial and does take 0 to 0. So that means that if you have a minimal map, you might as well assume f of 0 is 0. So look at what happens here. You have a certain bad set, things that can't be written a certain way, and then you throw in the extra condition, f of 0 is 0. You eliminate the triangular number 1. So you're not allowed to use the number 1 anymore. You're allowed to use 1 or 0 as a coefficient. Okay, so anyway, you get this thing. And then let me go back. I forgot to say the last line. In general, there's no way I don't know, maybe 19th century mathematicians would have been able to do this, but you're going to get a binomial, some kind of binomial coefficient, and you're going to ask, depending on the source dimension. And then you're going to ask, what are the possible numbers that can be written as written as sums of unique numbers from that set? And one of the reasons why I'm saying this is that you get into the weeds of combinatorial number theory by this simple question about CR maps between spheres. Okay? And I'm not sure it's the right thing to do, but what I want to know is which is going to happen. Number theory and combinatorics is going to tell us something about CR geometry, deal. Or CR geometry is going to tell those fields something. Okay? And I will say that for the degree estimate problem, it still goes the wrong direction. Combinatorics does the thing or whatever. But using CR vector fields, you never get the sharp numbers. So anyway, okay, now, I just want to remark. This kind of thing, I rediscovered a theorem of Ron Graham, Bell Labs from 1964. I just want to say a word about this. You have some polynomial that takes the integers to the integers. And you ask, look at sums of distinct values. So you take summation Cj, P of j, where Cj is either 0 or 1. And they call, a terrible term, polynomial complete if the set of points, if the set of numbers like this is cofinite. So there's a pretty simple understanding of a necessary and sufficient condition. So I'll skip that slide. Now I'm going to, what does it mean to be complete? I said it's a terrible term. It means if you look at the set of numbers, summation Cj, all right, look at the set Cj, P of j, where Cj is either 0 or 1. Look at the set of possible numbers. Is that set cofinite? That's what it's called complete if that set is cofinite. Now it's easy to check that binomial coefficients are cofinite, and that implies that for the unitary group, the theorem Ming and I proved that the set of gaps is cofinite. Okay. Right, so if you go back to that slide I had, even in source dimension 3, you get that ridiculous set of numbers. I'm not going to try to calculate that for higher source dimensions. I will say, in studying this, I think if I remember the number right, I'm not certain I remember anymore. If you take the polynomial x cubed, it's complete. The largest number that you can't get is either this or this minus 1. And there is a paper written in the late 1960s with the title, just this integer. So they actually prove, now of course using Mathematica or something similar, you can do this by coding, right? This is a small enough number. Okay, but anyway, that's what it means to be complete. It's a terrible term, right? Completeness means something different, but that's what it means. So, okay. So now I'm going to talk a little bit more about the recent progress. So if you have a monomial sphere map, so in particular, that's characterized by this group containing the torus. It's easier to say a lot of the same things. So when you take the squared norm of the map, you get a polynomial in the underlying variables x now. So that thing's called the moment map if you want to be pretentious. You just list the absolute values of squared of the variables. Then P of x is 1, and S of x equals 1 is the same thing that the underlying F maps the sphere to the sphere. Okay, but the advantage of this is that all the coefficients are non-negative, and the target dimension is trivially computed by, as the number of terms. Okay, so there you see where all the combinatorics is going to come from. Okay, so that's that. Okay, so the first thing, this is not difficult, but let P be a good polynomial degree D. That means it's one of these coming from monomial sphere maps. So it satisfies the conditions on the previous slide. Let me put that back up. P of x is 1 on the hyperplane. The coefficients are non-negative. I always assume it takes 0 to 0. And the number of terms I write by n of p. Okay? So there is a one-to-one correspondence between these polynomials and a certain compact convex subset of R to the D, where the number of terms in the interior of that set, so let me draw a picture, is here. I have some kind of a intersection of a bunch of hyperplanes like this, and I get some kind of closed, bounded set, in the interior of this set, there are lots of terms. The maximum terms possible for something of degree of that takes 0 to 0. That's what that slide is saying. And in order to analyze the gaps, what do you have to do? In principle, is you have to do the combinatorics of looking at every boundary point and seeing what happens for boundary points. Okay? And this is pretty brutal. However, I decided I was going to do this for the special case of quadratics. It turns out to be possible and gives new information about rational shear maps in general. Okay? In the special case where degree is 2, this set here, this compact set, this compact set, is just a 0, 1 cross itself n times. So how do you describe the boundary of 0, 1 cross itself n times? You have to tell the person the number of coordinates that are equal to 1, the number of coordinates that are equal to 0, and the number of other coordinates, and analyze all those cases. Okay. So this chart, so for each source dimension n, there is an array. Okay? So I have a function from integer value, I don't know what you call these things, interval valued arrays. So for each n, I write down some infinite array. Each entry is an interval. These intervals are exactly the set of capital target dimensions that you can get. Okay? There's one detail that I haven't completely filled in, but I'm going to try to say, here's what happens. So this is a special case of 20 variables. Okay? The identity map corresponds to all the, remember I've got 0, 1 to the n. I'm looking at the boundary. If I take all the points equal to 1, that corresponds to the identity map. All the unknown coefficients corresponds to the identity map, which has source dimension 20 and target dimension 20. Every time in 20 variables. So I get the interval 20, 20. Now, if I take one of the numbers equal to 1, that's the only, I'm on the boundary. Everything else is either in the inside or on the boundary or whatever. I get an interval from 39 to 40 that's possible. If I take 2 of them equal to 1, I get this interval, and so on. So something like this arises by assuming there are 3 points, let's see, 1, 2, 3, 4 points on the boundary that equal 1, in that 0, 1 to the n, and whatever number of zeros I can get, right, and I get an interval. So I get these intervals going this way. Now, I get this column. For any integer n, I get this column. Now, then I apply the postage stamp principle. So let me write this down over here. If I have some function f, it's a good polynomial. I write it out as a bunch of stuff, and then I isolate a single monomial that occurs in f. I'm going to assume this is of largest degree. I can get a new map that I'll call f tilde, leave this alone, take the m, and then multiply this by the sum of the variables, xj. So on the hyperplane, sum of xj equal 1, what have I done? I've eliminated one term and replaced it by n. So I've added n minus 1 terms. Okay? Or I could take, say, f double hat, where I take the single m, and I write m over 2, leave that there, or lambda m, but I'll just put m over 2, plus m over 2 times the summation xj. So in this case, I have the same number of terms plus n minus 1. Okay? So if you think about this, there's 2 ways, given a map, to generate a new map. I could take, this is a special case of some tensor product operation I wrote down years ago. It's special in the monomial case, but there's 2 ways to generate new maps. Now for any n bigger than 2, n and n minus 1 are relatively prime. So if I do this operation always on a term of highest order, I can get higher order maps with impact the number of terms. I can add n minus 1 or n. Okay, so if I take a valid interval and I add n minus 1 to the left and n to the right, I get valid intervals. So now I get more columns in this array. Okay, now here's the stunning thing about this. Look in the anti-diagonal like this. Let's do one more. Okay. For all n, obviously I've calculated formulas for these intervals. For all n, this anti-diagonal has no gaps in it. This one, for example, starts at 5759, but it becomes 5760. If you look at that guy and that guy is an interval with no gap. 7477, that goes from 74 to 77, but this one goes up to 80. So this guy gets replaced with 74 to 80. This guy, 90 to 94, those are two interstates in Chicago. That goes up to 96 to 1, right? 994 up to 97 to 99, 96 to 100, okay? If I take 105 to 110, that goes up to 115 to 120. But now, when I do that, okay, so on, okay? You see what I'm saying? This each anti-diagonal it's a union of intervals, but they overlap. Or they have the property that the endpoint of one is, just one more. So no gap. So I fill in these things so I can replace this with a new set of intervals. Now, everything I'm going to say is correct, except I have not given a completely rigorous proof that that you couldn't, by some other ridiculous method, although I proved it in lots of cases, come up with some other valid intervals, but this is completely consistent with the gap conjecture. What are the gaps in 20 dimension, according to Huang and G? They are exactly, okay, I don't get 0 to 9, I can't get 0 to 19, never appears here. I can't get 21 to 38, that never appears here. So I look at these numbers, and then okay, what can I get here? I can't get 41 to 56. I can't get, what was that, 60? I can't get 61 to 73. I can't get, that went from 90 to 100. I can't get 101 to 104. Maybe did I leave one out here? I think I did. I got 77, I got up to 80. I can't get 81 to 89. Okay? Now, this is what's true. This is what happens. So for any number of variables, okay, so what did I do? So beyond 104, this guy gets enough consecutive terms so that every term beyond that can be achieved by higher degree things by the fact that these two numbers, n and n minus 1, are relatively prime. So the largest gap here is 104. Here's all the intervals of gaps. Okay? Now, the formulas for these gaps, these things. Now, here's the stunning thing. It's actually possible to figure out what this number 104 is. Okay? It's unbelievable. I first take the source dimension n, and I calculate 1 plus the square root of 8n minus 15, divide by 2. That's not necessarily an integer. I take the floor of that integer. It turns out, as an exercise, if you're bored, try to prove that that's the same as the ceiling of that number. It's not completely trivial, but it's true. Okay, then you take that number s. Then you plug into that formula s of n times 2n plus 1 minus s of n all over 2 and subtract 1. That's the largest gap. Okay? So, anyway. Let me just go on a little bit. Okay? So, I don't think there might be a typo in one of the top two. I remember when I sent an email to some people about this. But here are the gaps for source dimensions up to 12. Okay? I don't want to look at that too much. But okay, now I want to see just a little bit more about this. In 100 variables, these are the numbers. But there's another way to think about this, which is quite interesting. These intervals in the first column correspond exactly to the possible target dimensions for quadratic maps. And it's a theorem that everything of degree 2 is spherical equivalence monomial. So this is exactly true for quadratic rational sphere maps, is exactly the same problem. Okay? Okay? So if I go down here and I go down far enough, actually halfway to the end of what this would end, this diagonal over here hits the next diagonal, and I get a maximum number, the maximum gap for just quadratics. Okay? So if an n is, when there's 100 variables, the quadratic gap is 3774. And then what happens is, when you do this, you're allowing cubic polynomials, you lower that gap. When you allow these degree polynomials, you lower the gap. And then there's a number after which you don't get anything more, and you lower it down to that's the list of gaps when there's 100 variables. Now you'll notice that the left-hand side of each of those intervals is always congruent to 1 mod 100. Why is that? Because if I had 100 variables here, the gap has to end, anyway, I won't say it, I'll let you amuse yourselves. Okay, so anyway, that's what you get when you have 100 variables. Okay, now, so I decided to calculate, all right, so here's the theorem, right? For each number n greater than g of n, there is a minimal rational sphere map with source dimensional n and target dimension capital N. Okay? And it's just, this slide is saying that you can improve things. You already prove a theorem just by looking at quadratics, but you can get rid of some of the quadratic gaps. And that's the procedure for doing that. Okay, yeah, I'll skip that. Okay, this is all I've just said. Okay, now here's a stunning thing. For quadratic gaps, you can also find a formula for the largest quadratic gap. And they're the number. Slightly different formula, whether n is even or odd. Okay? But if you look at these numbers in order as a sequence, so you take n equals 1, you use the bottom formula, n equals 2, the top, n equals 1, you get a sequence of numbers. So this is what really, I won't bore you this. It turns out that this sequence is known. It's exactly the set of integers for k, such that 24k plus 25 is a perfect square. This connection to number theory just boggles my mind. So I'm wondering whether, okay, so I'm going to say a little bit more about that other thing with floor and ceiling. Okay. So for the quadratic gap, you get something or other that depends on whether 24k plus 25 is the square of an integer. In the general result, what mattered whether 8n minus 15 was a perfect square. So you see the nightmare of this, you have somebody who's trained to do weakly pseudo-convex domains, is working on this problem and discovering all these connections with whether certain expressions involving integers are perfect squares or not, and all this kind of thing. So I repeat the question, which is going to be true? CR geometry is going to tell number theorists something, or number theorists are going to tell CR geometry something, and to quote a song, I wish I knew. I don't know. So anyway, Now, let me just say one other thing in the next couple minutes. I have a few slides about a proof of this thing of those guys. I want to mention one other thing. Okay? So I have my usual monomial sphere map. Now, I think this is extremely worthwhile. When you're calculating the number of terms in these monomials, you are doing something that people do in engineering all the time, abstractly, but the connection would be not obvious. In engineering, signal processing and stuff like that, people have a linear system. The answer they know is a trig polynomial, say. But it's an infinite dimensional null space, so there's lots of polynomials that work. So they want to choose one to minimize the number of different coefficients, different lambdas. So in other words, they want to minimize the number of terms. That's exactly what we're doing here. We're solving a linear system, and we're trying to minimize the number of terms. Or in this talk, what are all the possible number of terms for solutions? So when I was a grad student, I TA'd a class. There's a bright guy in there, honors calculus thing, who became a famous statistician. He's got a paper that's been cited 18,000 times, okay? And it's extremely sophisticated. I couldn't begin to state the main theorem, except the corollary of the main theorem is the following. You have a linear system in large number of real variables. Null space is positive dimensional. You want to calculate the number of non-vanishing coefficients of all solutions, find the one with the fewest. And this theorem says that asymptotically, the minimum number of non-vanishing coefficients is generically equal to the L1 norm. Okay? So I decided I was going to compare. So I'm doing the same thing. I have a linear system. I'm interested in the number of terms. That's the sparse thing. That's the L0 norm, they call it in engineering. But the L1 norm is simply the value of my sphere map, my monomial map, at the point 1, where that means all ones. So that leads to the following problem. I'm going to not walk over there and get the eraser because Andy's running a tight ship. Okay, so here's a problem. It's ridiculous. Okay, I have a polynomial P of xy. Coefficients are bigger than or equal to 0. P of x comma 0 is x to the d. P of 0y is y to the d. Okay, and the degree is d. Degree equals d. And P of xy is equal to 1 on x plus y equals 1. That's my setting. And then I'm making a certain assumption that certain monomials occur. Okay? N of P is the number of terms. And P of 1 is the sum of the coefficients. Now, stunningly enough, I solved this problem in all dimensions except 2. And if any of you solve this in dimension 2, I will rewrite Paul McCartney's song, Maybe I'm Amazed. I had Lichtblau code this from, I solved this linear programming problem for each degree D. I solved it up to degree 11 or something by hand. There's like pages of computations. So Lichtblau, using very sophisticated tools of mathematics, some of which he wrote, coded this for me up to degree 202. So in each degree D, so the goal, let me just fix the picture. My goal is to, given all this, I want to minimize P at the point 1, 1. Okay? I know a huge amount about this problem. For each degree D up to 212, I have an answer. I have a general result about monotonicity, bounds, asymptotics. Blah. But do I say more? Okay. Anyway, in dimensions other than 2, I know it, but I just get to this slide. In 35, degree 35. So this is a polynomial in 2 variables. It's degree 35. The minimum is some number that grows with D. But if you take twice the degree plus 2 minus the number, then it becomes a controlled number between 2 and 4. So this is the number. That's what it is. For every degree, The rational number that you're getting that solves this linear programming problem has huge numbers of digits in both the numerator and the denominator. Ridiculous. For degree 212, you can't even write this out on a page. It's like takes real pages to write out the formula for the integer. So anyway, in dimension 3 and higher, completely solved the problem. Dimension 2, spent hundreds of hours on it, and I have no idea. I mean, I proved all sorts of things about it, but okay. Anyway, so I'm basically going to stop here, but I want to go back to the slide about this principal conclusion of this talk. Is that I should have jettisoned this talk and given an impromptu talk on what Dave Catlin really meant in his papers. Because this talk is just the weeds of, I mean, it's just ridiculously complicated in technical combinatorial number theory that arises very naturally in CR geometry. So I'm sure there are many people in the world better equipped than myself to solve some of these, but it is what it is. Hasta Salas.